Okay, so welcome everyone. And so my project is on electrostatically levitated object handoff to minimize wear and particle generation. So particle generation and the related defects and loss of productivity remains a critical challenge for the semiconductor manufacturing industry. And object handoff. So what do I mean by object handoff? In semiconductor manufacturing, we have wafers and reticles. We'll look at what those are in more detail subsequently. A handoff typically means there are so many manufacturing stages and handing the object off from one manufacturing stage to the other. So we built an electrostatic levitated handoff system. More specifically, what we did is we use electrostatic levitation to transfer the object from a pickup stage. So if it is on the resting pins over here to the electrodes, which is on the other stage. And we transfer the object by electrostatic levitation such that it's levitated, it's stable in 6 degrees of freedom. We also create a bow such that it contacts at the center first and then clamps upward. This is a video of the system in action. It's a bit hard to see, but you will see that once it's levitating, the gap will separate. And this is the floater that we are levitating, and this will go up and clamp. These are the corresponding signals. Blue is the Z direction. Orange and green are theta X and theta Y. And then purple is bow. It's, I think, hidden here, but it will show up pretty soon. So let's look at the video. I'll play it again and then walk you through. It's clamped now. And now will be the unclamped sequence. Yeah, so now it's unclamped. Let's just look at it again. So when it is making contact, it first contacts at the bow. So you can see at the bow, and then now it's fully clamped. And even while releasing, it loses contact at the center last, and then it gently comes down.
Brij, sorry to disturb you. I think your screen is not shared on Zoom.
Oh, thank you. So my screen was not shared on Zoom. I apologize. Okay, is this better?
You can see it now. Yes.
Okay,
Please
sorry. Yeah, I'll just continue from this point on. I apologize. Okay, yeah, so this is just some pictures of rest of the setup. These are the electrodes which generate force on the floater. And then we look at more details. So why do we care about how objects are transferred? Why is it even important? And to understand that, we have to look at the growth of semiconductor manufacturing. In the past 50 years, from 1970 to 2020, the number of transistors on a chip have doubled almost every 2 years. It's commonly represented as the Moore's law, which is not really a law per se, but that's been the trendsetter for the semiconductor industry. So if we see in the past 50 years, the number of transistors that are fit on a chip that we have in our phones or in our computers has increased by almost 100 billion times. And a key step in the semiconductor manufacturing process is photolithography. And so photo means light and lithography means printing with light. So we have a photomask, also known as the reticle, which contains the patterns we want to expose or not expose. So it has the circuit, it has the image of the circuit pattern that we want to print, and then light is shined over it. So those regions where light shines, the resist, it's a photosensitive coating, it undergoes a reaction and it either hardens, in which case that'll remain and all the other components would go away and we will have a layer like this, which is called a negative resist. In other cases, it would soften and that region will go away and we will get a cavity there and all the other regions still remain the same. So that's the, that is photolithography in very short. And a key objective of photolithography is we have the smallest size that we can print is directly proportional to the wavelength of light. And hence the trend towards smaller and smaller wavelengths of light. In the most current generation of photolithography machines, we use a 13.5 nanometer wavelength of light, which is almost soft X-rays. This is an example of a reticle, which is what we finally want to levitate. And yeah, we have a reticle here, which I can pass around. But a reticle is essentially a 6-inch by 6-inch glass substrate, which has the coating on top, which contains the master pattern that we want to print. And it has a conductive electric layer, and that's how it is clamped using an electrostatic chuck on the exposure stage. So I can pass these around. So as I mentioned, we are moving into extreme ultraviolet lithography, 13.5 nanometer wavelength of light. And at that wavelength, even air absorbs that radiation. And therefore, we have to operate this machine in vacuum and use reflective optics, which further exacerbates the particle generation problem. Every time we have to print a new layer, so the reticle is up there. We have the light source here. It reflects from the reticle, and that gets printed onto the wafer. And that's tagged layer by layer by layer. Whenever we want to change the print pattern, we would need to exchange the reticle, swap them out for the new reticle, which has the new pattern that needs to be printed. And there are published results which show that the number of exchanges, the more number of times we exchange the reticle, they cause particle generation, and that has direct impact on loss of productivity. How does reticle exchange take place? We have a reticle stacked on the magazine here. So we have the inner reticle handler that transfers it onto vacuum. And then we have the reticle, which rides on a short stroke stage called reticle stage here. So the reticle is clamped to an electrostatic chuck and then moves on drives, and it comes and then picks up the reticles. Why does the current reticle exchange process generate particles? So to look at that, let's see what happens currently. Say the reticle is on the handoff stage. It's currently resting on these pins due to its own self-weight. Now these reticles, because they are working with such small nanometers, such short wavelength of light, and the fact that the optical features are so small, they are flat to nanometers. So they are extremely flat, and they have a slight bow of about 1 micron just due to its self-weight, and even that is significant at the kind of precision that we are talking about. So the electrostatic motor, so the free reticle stage comes and aligns itself vertically. Then as it comes down, it makes first contact at the center, at the corner, because flat on flat contact is non-deterministic. It's very hard to make full contact. We invariably contact either at the corners or at the edges. And then further, so once we think we have made full contact, we turn on the electrostatic chuck. But what happens is, because we had that initial bow, the edges then are sheared outward, and that further generates particles. So we have particle generation due to the initial impact, and we have further particle generation when we are shearing the bow mode and making it flat. So what is our proposed solution? We propose to isolate the reticle such that once it's levitating, this pickup stage, any vibrations in this stage do not matter anymore. The floater is isolated, the reticle is isolated. Then we levitate and make first contact at the center, making an upward bow, and then clamp outward, thereby minimizing any shear motion and generation of particles. To achieve that, we need to be able to achieve the following. First is we need to stabilize the floater position. So floater and reticle I'm using interchangeably, and I'll explain why in a moment. So we need to stabilize this floater in 6 degrees of freedom, and we are changing the gap from 250 microns approximately all the way to 0, and then making contact. So the levitation must be stable across a range of air gaps. We make first contact at the center, and then we have to be able to also control then the flexible bow mode. And I think one of the most critical things is we have to prevent any sort of discharge for 2 reasons. One, if there is any discharge event, that will further generate particles because it will vaporize material from the reticle surface. And second, it will deposit charges on the reticle, which will then be prone to attracting any dust particles from the surrounding environment. So for both those reasons, we have to prevent electrostatic discharge. The constraints are, we wanted to do the experiments in air. The final setup would work in vacuum on the machines that we saw earlier. But we wanted to limit our experiments in air because it would be much easier for an experimental setup to work with air. And we can still prove the feasibility of the concept that way. Now, because we are working in air, we are limited to much lower operating voltages, which in turn means that we cannot levitate the reticle that I've passed around, and we have to work with thinner floaters. So for my experiments, I used 400 micron thick aluminum sheets as my floater. So what is the main message? So in object handoff, in the previous way in which the pickup was happening, we had 3 body contact at the same time: the pickup stage, the object that I want to transfer, and the handoff stage. All of these were coming in contact at the same time. 3 body contact is non-deterministic. It's very hard to control where exactly contact is happening and the contact forces. So what we do is we isolate the contact such that the object of interest is either contacting the pickup stage or is contacting the handoff stage, and in between it is isolated and controlled. Its position is controlled by levitation. So the remainder of my talk is divided into 3 sections. First, we look at prior work and how this work fits in and expands the existing literature. Then we will look at the design of the levitator, followed by experimental results.
One short question in that previous slide. Why is there plastic on the microphone?
Yeah, so this entire frame is grounded. So just for people on Zoom, the question is, why is there this plastic film on the micrometer? The reason for that is this entire frame is connected to ground, so it is grounded. When I apply an electric field, and so the floater then has electric field on it. If there is electrical contact, the floater was tending to get charged. It was picking up a charge because of at the time when it was breaking contact, and therefore I had to insulate it such that it's always electrically floating and it has no contact electrically.
That's one I hadn't picked up on.
Okay, so moving on. Yeah, so prior work on macro scale electrostatic levitation, it has a relatively recent history. The first published work was in 1992 by Kumar et al., where they used an LCR oscillator where the floater with the electrodes forms a capacitor, and then it's a tuned LCR circuit such that at perfect tuning, it is at the height that we want to levitate. If it goes further away, the capacitance reduces and it also, the voltage or the oscillation voltages increase, tending to bring it back. And if it goes further up, the oscillation voltages reduce, tending to bring it down. And that's how it was stabilized. So this was passive. It was not possible to easily control the height of the floater. A significant body of work in macroscale electrostatic levitation was done by Professor Higuchi's group in Japan from the mid-1990s to mid-2005. And their objective was to develop systems for object transport, non-contact object transport in semiconductor manufacturing, such as silicon wafers or even glass panels in glass panel manufacturing. So they did a lot of work building up to those things. So they levitated silicon wafer and an aluminum disk, and they controlled the position in 3 degrees of freedom, z, theta x, and theta y. And all their experiments were at a constant height because they were more interested in levitating it at a constant height and then transporting it in the factory, for example. This is an example where they are both levitating as well as transporting an aluminum disk. They also levitated dielectrics, which is actually quite challenging and different from levitating conductors, because in conductors, it's easy to have free charges right at the surface. Whereas with dielectrics, all the charges are bound, and therefore we have to create strong field gradients. As you can see, they create strong field gradients with multiple fringing electrodes, and they were able to even levitate dielectrics, which I think is fascinating. And they also made levitation and rotation motors using both variable capacitance mode as well as induction mode. And Nino et al. In 2000 actually levitated a 20 millimeter thick aluminum disc, so quite heavy, almost 400 or 500 grams, at 200 micron air gap. And they used very strong field gradient, 15 megavolts per meter. So this is a good sort of precedent to show that such levitation in vacuum has been done and could be a feasible concept. So what does this work do? And so our project expands on the previous literature. One, most of the previous studies that I talked about levitated at a constant height, and we have stable control across a range of air gaps. Further, they only control the rigid body directions, that is Z, theta X, and theta Y. We also control the flexible bow shape. And then we do all of that to be able to do the pick up and place down sequence, which I think is new in the body of literature. And an interesting result of this work was we found that we are able to operate at much higher field stresses than is usually thought possible. In air, normally the dielectric strength that is reported is 3 megavolts per meter, but I will describe in subsequent slides, we operate for a short duration with up to 11 megavolts per meter without any discharge event. And I think that was quite interesting. Okay, so design. This is the setup. And so we use first surface mirrors as our electrodes. I have some first surface mirrors here, which I can pass around. It has this blue coating and the mirror is just behind this blue coating. So you can peel off one of the corners to really see. Yeah. Okay. And so the reason we use first surface mirrors is normal mirrors have a reflective coating on the backside and they're not very precise. Whereas in first surface mirrors, the coating is on the topmost surface and their flatness is very tightly controlled. So for example, the mirrors that I'm passing around, they have a flatness of 400 nanometers per square inch. And it is quite inexpensive to obtain these mirrors. And therefore, it was a good option to use as the electrodes. We just mill out wherever we want to remove the layer, we just mill out certain regions, create islands, and those islands work as the first surface mirror electrodes. Then we stick a layer of capacitance sheet for insulation that acts as a dielectric insulating layer. And we use the aluminum floater as our object. We sense from the backside. In the final setup, we would like to sense from the front so that all the references from the pickup stage. But we decided to sense from the backside because that would save us from drilling holes into glass and it was easier. And also we can still show the levitation successfully that way. These 4 micrometers at the 4 corners help to adjust the initial air gap and the initial orientation of the floater from the electrodes. This is the hardware in the actual picture of the hardware. So we have the top plate, which we call the actuation plate. That is where the first surface mirrors are stuck to the top plate. And then the bottom plate, we call the sensing plate because all the eddy current sensors are mounted on that plate. To be able to align and have a repeatable system so that we can make some modifications and then put the system back together, we use a kinematic coupling. So there are 3 micrometers with balls at the end with grooves. And therefore, if I want to make any change, I can just pry open the top surface and then put it back together within a few microns. The system is repeatable. Okay, so dielectric discharge. So normally in air, the quoted electric field strength is 3 megavolts per meter. And this comes from the studies done by Paschen, also known as the Paschen curve, wherein so the x-axis here is both a product of pressure and displacement. So this is studying the effect of at what voltage does breakdown occur as I vary the gap or I vary the pressure of the medium. So what we see is, let's say we are fixing the pressure to 1 atmosphere. As I'm reducing the air gap, the amount of voltage that I need to break down reduces, reaches a minimum, and then it seems that it exponentially increases. So it turns out that Paschen, while doing his experiments, only came down till about 100 microns and in distance. And to the left of this 100 microns, the plot is by reducing the pressure of the gas. So we still don't know what happens at a small gap. The mechanism of discharge in this region is the Townsend avalanche discharge. And it turns out what happens is that small air gaps, it's a different mode that causes discharge, which is field emission. And that is shown on the graph to the right. And this was compiled by Babraskas in 2013. So there are numerous studies which show that, so this is at 1 atmosphere. As beyond around 10 micrometers, we follow the Paschen curve. So Townsend avalanche is the prominent mode of discharge, but less than about 10 microns, the field emission begins to take over, and that is the most significant mode of discharge. And the field strengths that we can achieve there are quite high, close to 100 megavolts per meter. But still, in our setup, we go up to 200 to 250 microns. So we are still limited by Paschen, and it seems that we would be very prone to discharge, especially at large air gaps. But it turns out that because we are using a dielectric insulating coating on top of our electrodes, for short durations, we can use much higher field strengths. And the reason for that is because, for example, Captain, the dielectric has a very high dielectric strength of 300 megavolts per meter, and its charge relaxation time constant, that is the time constant or the time it takes for the charges. If I represent some charges here, how long does it take to be reflected on the other side? That is of the order of 8 hours. And since our levitation happens in the order of a few seconds, for short durations, we can have very high field strength without any discharge. So what is the maximum field strength that we achieve in our setup? Okay. Sorry. Okay. That happens when I create the bow at small air gap. At that point, the entire weight of the floater is only supported by the center electrodes. So all the other electrodes have very low voltages. The center electrode is at the maximum voltage possible, which is around 400 volts. And I have field strengths of 11 megavolts per meter in that small region, but still we do not have any breakdown event in that short duration. So there are two things to note here. One is the time constant of the motion has to be much smaller than the charge relaxation time constant. And number two, there should be no sharp changes in voltage because we want to operate as close to DC as possible. If there are sharp changes in voltage, there are displacement currents induced, and that can cause charges to flow through. And in fact, that is used with AC current. If you are driving with an AC current, that's commonly used to create something known as the dielectric barrier discharge. And that's used for ozone generation and air purification applications in industry. Okay, so now that we know that we won't have breakdown, we design the electrodes. So this is the electrode layout. We have what we call the main electrodes, which control the Z, theta X, and theta Y, which are these 4 quadrants here. And we use equal and opposite polarities because we want the floater to be net neutral in charge. So we want to have equal electrode areas of both positive and negative, such that when I'm actuating, the floater can be charge neutral and still have forces on them. The center electrodes, both positive and negative, are at the center. Then I have ring electrodes, which we call the ring electrodes, which are these small thin electrodes at the edges, and they generate forces by fringing fields. And because they generate forces by fringing fields, the floater is aligned such that the edge of the floater is aligned with the outer edge of these ring electrodes. So this is just an animation. We can see that for horizontal forces, it's only the electrodes at the edges that matter. So we use thin electrodes at the edges to generate the horizontal forces that are needed for stabilizing the horizontal modes. Then the question is, where do we sense? We also have a ground strip all around to make sure that fields do not go beyond the surface of the electrodes. So then now the next question is, okay, once we have the electrodes, where do we sense? And that I will talk about in the next slide. To identify where the sensor should be placed, we use FRF analysis, which is frequency response function analysis. We did this using Nastran solver. So this is the floater, and we have an image of the electrode pattern on the floater. There are the 4 quadrants and then the center electrode. We excite one of the quadrants with a sinusoidal pressure wave, and then we see the response that are points of interest, which would be the points at which I will place my sensors to see what the response frequency function looks like. So in this example, I'm showing the final positions that we selected, which turns out the best positions are at the center of each quadrant. And then we get the response like these. So it shows behavior of all the modes as well as the phase response. Once we have that, so suppose I want to get the z direction from these measurements. We take the average of these 4 quadrants. That gives me the z direction. Theta x would be the average of these two minus these two at the bottom, so on and so forth. So I can transform these coordinates to get the z, theta x, theta y, as well as the bow direction. The bow direction is the center measurement minus the average of these 4 quadrant sensors. So interestingly, when we combine all of them together, in the z direction, all the modes disappear because of the symmetry of how we are placing the sensors. We have no modes that show up. And why is this important? Because especially in the z direction, as the air gap reduces, due to the increasing negative stiffness, I have to achieve a high crossover frequency. And having no destabilizing modes gives us confidence that we can achieve a high crossover frequency without much challenge. In the rotation directions, so we want to achieve a crossover frequency in vacuum of around 100 to 200 hertz. We do see a zero pole effect, but it has sort of a phase boost, and that is beneficial. So it's not very detrimental. Yes, sir.
How sensitive is the cancel to the center position of those 4 sensors? Is there a 5 millimeter? Is it noticeable, or do you have some measure of the sensitivity at the position of those meters?
Right. So the question is, how sensitive is the sensor position to this mode cancellation in the z direction? And the answer is, I tried to first work with a fine grid and try to make them as coarse as I could. And so this is with a 5 millimeter grid, and within a 5 millimeter radius, if I select points which are close, because it's very hard to select at the center anyway, it will select a node which is closest. It was still able to cancel reasonably well. Okay, so we looked at z, theta x. So these are the flexible modes. So we have the torsional mode and the bow mode. And yeah, so it shows a stiffness behavior, which is to be expected because it's a flexible mode, and then various resonances after that. I show the torsional mode because we can sense the torsional mode, which is just the twist of the floater, but we can't actually control it based on our current design. And yeah, I can explain why that is if there is interest.
I understand, for example, the bow model, the iron bones have about the same Q factor as the balloons. I would expect that not to be the case. I would expect the handles to go really quick.
Right. Yeah. So this is just the software. There must be an option, but I did not know how to have damping ratio based on the modal frequencies. So I just have set a constant damping ratio, and that is why. So the question is, in the bow mode, at the higher frequencies, the peaks still tend to be very sharp, but in reality, damping will be higher at higher frequencies. So we would expect the peaks to be much better damped. And the reason is, it's in simulation, I just set a constant damping ratio, and that is why the higher modes are also showing up. But yeah, question. Okay, so for the horizontal modes, we get the horizontal forces with x displacement. Because we want to passively stabilize the horizontal direction, we want to know how stiff is the system to any deviations in the horizontal direction. And we obtained that by using FE analysis using FEM software. We have the ring electrodes here at the 2 corners, and this is the main electrode at the center. The main electrode is set at 500 volts, and the ring electrodes are set at 1000 volts. And then we move the floater from left to the right and see what are the horizontal forces, which are plotted on the top right over there. I don't know. Yeah, so this is the system in motion. So again, as we saw earlier, most of the horizontal forces occur due to fringing fields from the ring electrodes. And this is the kind of force behavior that we get for small deviations in the x direction. It's almost a linear response. So it's a stabilizing, it acts like a stabilizing spring. And then for large deviations, because the fringing fields have now gotten stabilized, there's no more change in fringing fields for sufficiently large deviations. The force tends to reach a maximum saturation value. But we are interested in small deviations about the nominal point, so we can estimate the stiffness from the linear region. In the setup, we keep the ring electrodes at a constant voltage. So as the air gap reduces, the stiffness increases. Whereas the main electrodes, they reduce in voltage because we have to keep the same electric field for compensating the mass of the floater. So with reducing air gap, the voltages of those electrodes reduce.
So if you keep the ring electrodes at constant voltage, does that mean that they get close to breakdown as you go to zero?
Yeah, so the question is, if we keep the ring electrodes at constant voltage, do we get close to breakdown as they go to zero? Yes, but we don't see any discharge event because, again, we have observed that there was no discharge event because of the dielectric layer. Okay, to obtain high gains, we have to have low sensing noise, and we achieve lower sensing. So we use eddy current sensors, standard eddy current sensors, as our. So these are just standard industrial eddy current sensors. They're in fact, their intended purpose is not even to be used as eddy current sensors. Their intended purpose is to be used as switches in industry to know. But these are analog sensors, and by oversampling and averaging, we are able to make them work as very good low noise positioning sensors. We get a positioning noise of 56 nanometers, which I think was very helpful, because otherwise we would need to use a capacitive sensor, and each capacitive sensor costs around $3,000, whereas each of these costs only about $100, and we have to use so many of those. We custom designed and built our own high voltage amplifiers. We have with the 415 volt range, with a 20 milliampere current drive, with a 200 kilohertz bandwidth at 10 nanofarad capacitance. So the amplifiers are stable for any capacitive load. As we increase the capacitive load, just the bandwidth of the closed loop of the voltage control loop reduces. Yeah, this is just. So we use 6 of the amplifier stages for driving the 6 electrodes, and the ring electrodes are controlled by these 2 PCBs. So we have talked about all aspects of the system, and now I will talk about the experimental details in subsequent slides. Yeah, so yeah, we just machine out the non-conductive regions, and these islands are then the conductors. So we have the main electrodes and as well as the ring electrodes all around. The experimental results. Yeah, so I guess the key takeaway from this is we run our control loop at really high, at around 100 kilohertz on the FPGA, and then buffer all the data onto the real time, and then all the user interface happens on the Windows computer. This is the characterization plot of the eddy current sensor. It is nonlinear with distance, which is typical of eddy current sensors. But for a range between 0 to 0.6 millimeters, it's sort of linear. And we just use this range for our experiments. And the gain there is 0.2 millimeters per volt. Okay, so then we measure the plant body plots. So this is the system in levitation at an air gap of 150 microns. So the way we measure this matrix of body plot is we give an excitation. Let's say we excite in the column. So we give an excitation in the Z direction, and then I measure the response in each of the other directions. So I measure in Z, theta X, theta Y, bow, as well as the torsional direction. And the objective is that we want the system to be decoupled, and therefore the diagonal elements should be pretty strong. They should have a high magnitude relative to the off-diagonal components. What we see is that for the rigid body modes, that is Z, theta X, and theta Phi, we have relatively good decoupling, and they get decoupled really well. Whereas when it comes to the flexible modes, they are a bit more difficult. They have strong coupling to the other directions as well. And the torsional mode, we are not even controlling, but this is just data to show how it is impacted by the other directions. Then we measure the plant body plots with air gap. This is in the Z direction. So there are three things to note here. The first is the plant magnitude increases with increasing air gap. That is because the impact of air damping reduces as the gap is reducing. At low frequencies, the plant is dominated by the negative stiffness effect. So it has a slope of 0 and a phase of negative 180 degrees. At medium frequencies, it's due to the damping from air. So the phase goes up to almost negative 90 with a slope of negative 1. And then at high frequencies, mass becomes dominant, as well as we will see later, stiffness effect from the air film begins to dominate, and we have lower magnitude and phase. This is the return ratio, which shows the crossover frequency and the phase margin. So we design, so we use a robust controller such that our crossover frequency reduces with reducing air gap, but we are still stable across all the entire range of air gaps that we want to talk about. A key thing to note is that all of these plots are going down, which shows the negative stiffness behavior, but at 50 microns, this begins to go up. And that is because we have actually made contact at some location. And now it's not negative stiffness anymore. There is actual stiffness due to contact. And that is to be expected because it is very hard to maintain something perfectly flat, and plus our floater is very flexible, and therefore it ends up making contact at small air gaps. We use PI controllers with a low pass filter as our controller for all the controllable degrees of freedom. This is the return ratio body plot for each of those, for each of the control degrees of freedom. We achieve a 60 Hertz crossover with a 60 degrees phase margin. These are the results from, so when I'm just levitating the floater in the stably at a given air gap, what is the noise level? So in the Z direction, our noise is less than 200 nanometers peak to peak. And in theta X and theta Y, we are less than 0.2 millidegrees peak to peak. Again, this is the pick up and place down sequence. A few things to note here are at the time of contact, we have a bow of almost 40 microns, and that is where it makes first contact. That is why there is a slight change in angle, but once it's levitated, otherwise the angle is maintained close to 0 degrees throughout the levitation, and then it goes and clamps. So note that this takes around 8 seconds, whereas declamping takes much longer. And the reason for that is when we are clamping, we are pushing air out using electric fields, whereas to declamp, it's only the weight of the floater that has to create vacuum to bring it down, and that is much weaker. So it takes much longer for the initial duration of separation. So again, we separate last at the center, and then we bring it down. So yeah, so we separate last at the center, then we are levitated, and then we come back to resting on the pins. We also modeled the behavior of the air film, the dynamic model of the air film in the air gap. It turns out that at low frequencies, air acts like a damper because air has sufficient time to escape from the edges. But at high frequencies, because it does not have sufficient time to escape from the edges, it begins to act like a pneumatic cylinder and shows a very strong spring stiffness effect. So we used models that were published by Blech, and we just used that and modified that to be used in our system. And once we incorporate those results, that is the damping and stiffness due to air, along with the model for parallel plate capacitor, our model matches reasonably well with the actual measured plant frequency response. And I think this was helpful. So from the parallel plate capacitor model, we get the negative stiffness and the electromechanical force constant. Then we have mass of the floater and an additional phase drop because of the oversampling and averaging that we are doing. We also tried, I passed around the floaters with holes. We also tried levitation with a floater with holes. And now, so here, for example, air at the center has to travel almost half the length to escape, whereas now it is only the distance between these two holes. So we expect damping to be significantly reduced. And yes, the effect of damping is significantly reduced by almost 5 times. The plant has 5 times greater magnitude, but we didn't do more experiments from this because it was very hard to get rid of all the burrs from the numerous holes that we drilled, and that was creating scratches on the dielectric every time it would clamp. So we did not proceed with too much with this floater. So yeah, so just to review, we looked at the prior work and we talked about the design, primarily the dielectric, that we can work with high voltages without breakdown. And then we looked at the actuator and sensor design and then experimental results. To translate this into vacuum, we need to do 2 things. We need to change the sensing to happen from the chuck side so that it's all isolated and all the reference for measurement and actuation happens from the pickup stage itself. And then in vacuum, we can use even higher field strengths, which we have to because we are using the reticle. So we would need, for normal levitation, we would need a field strength of around 10 megavolts per meter, which is well within what is possible, even at 1000 pascals of pressure. As we go to lower pressures, which is what happens in the actual UV machines, this part of the curve shifts further to the right. So this just shows our feasibility of, it's feasible to implement this in vacuum. And it only gets better as the vacuum becomes stronger. Okay, future directions. Yeah, we can add capacitive self-sensing. We could also control the torsional mode. To do that, we would need to, so if this is my electrode, then I would need to make each electrode positive and negative. That way I can control each quadrant independently. And that way we can control the torsional mode as well. And then yes, of course, we need to test in vacuum. Now this concept of levitated handoff is quite general. We could use different force fields such as electromagnetic, pneumatic for other applications wherever object handoff is critical. So to wrap up, I hope that next time that you are faced with a task where you have to hand off an object and particle generation is critical, you will think of levitation, isolating the handoff using levitation, and then making contact at the center and then clamping. So I guess levitate, isolate, bow, and clamp. And that's the end of my presentation. Thank you.